So if we want to develop a motion for a humanoid robot, then we need first to understand the geometry of the robot. And that we can model using either rotations or translations for the actuators, as well as translations for the links. And then those can be modeled using homogeneous coordinates, which is why we're interested in those. So in the class today, we're laying the foundations for what we're going to do next week, which is introducing the kinematics. At the second part of the class, we want to do some programming with matplotlib in order to draw certain figures. Now we're going to start slow, and I'm just going to have this figure here, which is a simple arrow, and we can draw it using matplotlib, using code like this. So we use the plot function of matplotlib, which draws a line. Then we need to draw the rectangle, the triangle, and then the little square. The coordinates of those give 0, 0, which is the origin. And at the moment we're still drawing in 2D only. Then 1, 0, 1, 2, 0, 2, 0, 0. So if you look at the figure, then this is here 0, 0, 1, 0, 1, 2, 0, 2, and 0, 0. To go back, if I draw lines between those 5 points, then I get this rectangle. And I guess I can make it a little bit clearer by specifying the line colors. Then we end up with this figure. And so the triangle in blue, the rectangle I just mentioned in red, and the square in green. Now, let's say I'm talking, or I'm trying to generate some kind of drawing program. Then how do I change the position of the error, and what happens if we want to make the error not point upwards, but for example point to the right, to the left, or diagonally up, or an arbitrary angle. Now the first problem, when we change the position of the arrow, then that's called the translation. Second problem requires the ability to rotate the shape. Now, I don't want to do too many calculations and have this special purpose. Of course, if I wanted to rotate by just 90 degrees, then it's easy enough to figure out how to swap the coordinates. But we want to be able to do that for arbitrary coordinates. And the reason why we're interested in that is because later on, when we talk about the motion of the robot, then we use the same approach in order to relate the joints and the links of humanoid robot to where it is in the world coordinate system. So that problem then leads us to the forward kinematics problem. So let's have a look at rotation. And I'm going to go through the full proof for rotation. So why is this not working now? Not a string, a byte-like object. Maybe something changed here. Ah. Oh, sorry, that's not a rotation, that's a translation. Example. And that's the simplest problem. So if I have a point 2, 3, and I want to translate it in the x direction by 3 units, in the y direction by 2 units, then what will be the end coordinates of that point? Or let's take ty1. Then we end up with a 0.54. So that's pretty straightforward. If I've given a point P with the coordinates Px and Py in 2D and I want to translate it by a vector T which has components Tx and Ty, then the new coordinates are going to be P dash x is Px plus Tx, dash y is Py plus Ty. And if we're dealing with 3D, then we can extend it to the third dimension. So now let's have a look at rotation around the origin. This is a little bit more interesting. So I have a point PT that rotates by an angle alpha around the origin. So origin is here on the left. Then I end up with a new point PT dash. And the question is, if my original point PT has coordinates x and y, then what are the coordinates x dash, y dash for the rotated point? And how many of you actually know the answer to this? If you've taken any graphics or computer vision course before, then you will have seen this already. But I think it's still important to go through and actually prove the formula for this rotation, mainly because depending on your domain, there is two different types of representations. If you just Google without understanding what you're actually getting back, or if you're using ChatGPT, there's sort of a 50% chance that you will get the incorrect formulation. So let's have a look at this. Rotation of the shape around the origin, 0, 0. Given is a point PT, which has coordinates x and y. After the rotation by theta around the origin, what are the new coordinates of the rotated point PT? So this is theta, not alpha here. Sorry. So we rotate by angle theta. So we want to find a function f that has is a function of theta and x and y, and then spit gives us the new coordinates x dash and y dash. Now, without looking up the answer, how would you approach this problem? If we look at the figure here, then I've sort of given away part of the solution because I already drew in these blue lines. Now the blue lines, R and R dash, are indicating or sort of hint at the polar coordinates of the point PT and PT dash. Now the polar, in Euclidean coordinates, we give the distance from the origin to the point along some basis axis, x, y, and z. In polar coordinates, we give the angle from the x-axis to the point and the distance of that point from the origin. So here, point PT would have polar coordinates alpha, because that's the angle between x and the vector to the point PT, and distance r. And PT dash has coordinates r dash and alpha plus theta now, right? Because if I'm at alpha and I rotate by theta counterclockwise in the positive sense, then I end up with alpha plus theta as the coordinates for our rotated point PT dash. So to take Cartesian coordinates, not Euclidean coordinates, Cartesian coordinates x, y, and convert them into polar coordinates, I can calculate the distance, which is the square root of x squared plus y squared, the hypotenuse of x and y, and the angle would be arctan of y over x. Just to remind you, if you have to do calculate inverse tangent, it's always better to use the arctan2 function in Python or any other modern programming language. Actually, it says that in the next slide. So I'll just do it like that. So arctan or atan takes a single argument, y over x, atan2 takes two arguments, which means that it can deal. The problem with atan is that it doesn't work for vertical lines because delta x would be 0. So you cannot divide by 0. Also, you lose information and you're not sure about the quadrant of the angle, because if y is positive and x is positive, or y is negative and x is negative, you get the same angle back. It'll always be in the first quadrant, but by using atan2 it maintains the direction of the angle, so you get angles like 290 degrees. So let's see if we have the point in polar coordinates on what will happen to our point in polar coordinates. Well, the distance obviously will not change. Right? Rotating here, the distance r dash will be the same. Let me just send a message quickly. So if we rotate by theta, then r dash is equal to r, and alpha dash, the angle to the x-axis, would be alpha plus theta if we rotate by theta. Now we have the result in polar coordinates, then we can convert it back into Cartesian coordinates. Now, to take polar coordinates and convert them back into Cartesian coordinates, then this part here along the x-axis will be the cosine of alpha multiplied by r, and the y component will be the sine of alpha multiplied by r. So then I can calculate x dash is r dash times cosine alpha dash is equal to r times cosine alpha plus theta plus alpha, and y dash would be r dash multiplied by sine alpha dash, which is r times sine theta plus alpha. And so far we've used standard geometry, sines and cosines only, and their definition in a right angle triangle. So in a sense, this is already our solution. I mean, that is a function that allows me to calculate x dash and y dash if I replace r with the square root of x squared plus y squared, and then calculate the new cosines and sine angles here, then that will be a solution. But we can actually simplify this result using the addition theorem for sine and cosine. And how many of you still remember those? The addition theorems for sine and cosines. I'm sure you covered them in high school. But I actually want to go and prove it because in contrast to some other mathematical proofs in geometry that are kind of anticlimactic, this is a really nice proof and I really like it. So we're gonna go through it. So here is an addition of two angles. I have theta 1 and theta 2. Now the cyan line here, that line is 1 unit long. So that's a unit line here. And then the question is, how does that help me figure out what's the cosine of theta 1 plus theta 2 and what's the sine of theta 1 plus theta 2. But if I draw it like this, then it's pretty easy to see the cosine that I'm interested in, cosine theta 1 plus theta 2, if this cyan line here is a unit length. Actually, let me add that. X and Y. Okay, so X should be xt divided by 2. And I want to offset it a little bit to the left. So one character, 0.2 maybe. Yt divided by 2. And the string r is equal to 1. Where'd the 1 go? .1, so it'll be over here, so 0.01. Okay, so that looks better. So this is 1 unit here, that cyan line. So that means that the cosine that I'm interested, cosine theta 1 plus theta 2, is the red line here. Right? And sine theta 1, theta 2 would be the green line here. That distance. So now, how can we figure out cosine theta 1 plus theta 2? Move that up a little bit. So here's the red line that we want. then how do we find it? Well, then we have to figure out what the distances are. So if this is 1 unit, then what's the length of the blue line? The blue dashed line. Well, if this is 1, here we have a right angle triangle, right? And here we have angle theta 2, which means that the length of the blue line is the cosine of theta 2, right, multiplied by 1. Which we can ignore at this point. So that means that that blue line here, that line would be the cosine of theta 1 multiplied by this length, which is the cosine of theta 2. So that gives us the blue line from the origin to here, but now that's of course too long, right? We only need the red part of this, so we have to subtract this component here. So what's that component? Well, if we look at the figure and this part of the figure here, then the blue dashed line on top is what we need to subtract, right? Now, this angle here is theta 2. This is theta 1. This is 90 degrees minus theta 1. This whole angle is 180 degrees. So it's 90 minus theta 1 plus 90, 180 minus theta 1 is then this angle. So this angle has to be equal to theta 1. So that part here has to be theta 1. This angle from the red to this dashed, small dashed cyan line is also theta 1. Theta 2. Theta 1, 90 minus theta 1 plus 90. So that's 180 minus theta 1, and all of them added together have to add up to 180. So that means this has to be theta 1 here, this angle. Now, the small dashed cyan line is, if this is a unit length, then this would be sine theta 2. Sine theta 2. Now this component here would be sine theta 1, which is this angle here, multiplied by sine theta 2. Theta 2. So the thin dashed blue line is sine theta 2 multiplied by sine theta 1. So that gives us the addition theorem for sine and cosine. So we did the cosine here. Cosine theta 1 plus theta 2 is cosine theta 1 multiplied by cos theta 2 minus theta 1 multiplied by sine theta 2, which is exactly what we get here. So we have that. We can apply similar reasoning to get the addition theorem for sine. The sine theta 1 plus theta 2 is this green part here, the green line. We can calculate this green line by taking this thin dashed blue line and add the thin dashed red line to it. Right? This blue plus this red is exactly the same as this green. Now, this blue line here will be the sine of theta 1 multiplied by the cosine theta 2. And this part here will be the cosine theta 1 multiplied by the sine of theta 2. And that gives us the sine addition theorem, which is shown here. So I think this is really a very nice, elegant geometrical proof. So now I can put that into our formula that we had. X dash is r times cos theta plus alpha, y dash is r times sine theta plus alpha. So then I replace the cosine sum of the angles and the sine sum of the angles with our addition theorem, which gives us r cos theta cos alpha minus sine theta sine alpha, and r sine alpha sine theta cosine alpha plus cosine theta sine alpha. Now, if we go back to our original figure, the one that we started out with, then r, what is r multiplied by cosine alpha? Well, that's exactly the x component, the original x, right? So r cos alpha is x, and r multiplied by sine alpha, this red line here, that's the y. That's the same coordinate here. So that means I can replace cosine alpha multiplied by r and sine alpha multiplied by r with x and y respectively. So that gives me x dash is cos theta multiplied by x minus sine theta multiplied by y, and y dash is sine theta x plus cosine theta y. Now, here we have an equation for some, mathematicians like their formalisms, their descriptions to be extremely tight, extremely compressed. So we can represent this pair of equations in matrix form. So I can write it like that. Right here. X dash y dash is cos theta negative sine theta x and y, and sine theta cos theta, where this matrix here is called the rotation matrix. Now the reason why I told you to be careful is that sometimes you also see the rotation matrix in this form, cos, sine, negative sine, and cosine. And that is not necessarily wrong. It really depends on what you're trying to model. So in some of the geography applications, for example, this is a more natural representation, because which rotation matrix is correct depends on what actually rotates. In our case, we rotated the points. We rotated the points, so PT rotated from here to here. So the point moved. So in that case, our rotation matrix is correct. But sometimes you want the coordinate system to move. And if the coordinate system moves by an angle of theta counterclockwise, so I'm actually not sure how that looks like on the camera now, but if the coordinate system rotates to the right, then that's rotates counterclockwise, then that's the same thing as the points rotating clockwise, right? That'll be the same effect. If instead of the points the coordinate system rotates, then the direction of rotation is reversed, which means that the sign will swap its sign. So it'll switch from plus to minus and minus to plus, which is why sometimes you also find this rotation matrix. It depends on what you're trying to do. Do you rotate the points or the coordinate systems? Because if you rotate the coordinate system, then it's the same thing as the points rotated clockwise. Now translation, we had before we showed the equations for the translation. So x dash and y dash is x plus tx and y plus ty. Now let's try and represent those in matrix form. And what you realize is this constant term here, tx and ty, terms that do not depend on x, make it impossible to represent it as a 2 by 2 matrix. So what we can do is we need to add a third column here. And then we need to, in order for this matrix multiplication to be valid, the number of columns in the first matrix has to match the number of rows in the second matrix. Otherwise, your matrix multiplication is ill-defined. So that means we need to have an extra point here, an extra number, a third number. And that number will be multiplied by these constants, so we'll make it a 1. So in this case, now I get x, 1 multiplied by x, plus 0 multiplied by y, plus tx multiplied by 1, which gives me x plus tx. And here I get 0x plus 1y, so y plus 1 multiplied by ty is y plus ty. So that will be the correct representation of a translation in matrix form. But mathematicians are not happy with this kind of representation because they don't like non-square matrices to begin with, and then to have two different sized matrices in order to represent the translation and the rotation is not very nice. So they overloaded the representation and made it into into homogeneous coordinates and a 3 by 3 matrix. So now we can use a 3 by 3 matrix to represent both translations and rotations. So here would be our 3x3 matrix. We extended it just by adding a row of 0, 0, 1, which means that the bottom row here is going to add up to 1. Right? It's going to be 0x plus 0y plus 1 times 1 is 1. And on top, the top two rows are our translations in x and y. And we can represent our rotation. Now rotation, we really only need 2 by 2, but we extend it and also make it a 3 by 3 matrix. If we do, this is for 2D, in 3D we can do the same thing, except we need a 4 by 4 matrix then. So then here we can define a couple of functions. So here's our translation matrix. If I want to translate by tx, ty, then I generate this transformation matrix. And this is the transformation matrix for rotate around the axis Z, around the origin. And later on we'll look at scale and skew matrices, which are another type of affine transformation using homogeneous coordinates. So here we can then draw our arrow. First I had the function to draw the arrow, and now here are the coordinates of the arrow. And then I want to draw the... Now if you look at the function, I added an additional parameter here, a, which is abbreviation for this matrix that we want to apply to the points. And when I draw now the rectangle, I calculate the matrix product of my points multiplied by this matrix A. And I need to take our points from the that I want to draw, the rectangle here for example, and then I need to expand it, I need to extend it by adding extra ones at the bottom. So here I have the points in row format, so I need to transpose them first, then I need to add, to convert them into column vectors, and then add an additional one in the last row, an additional row with just ones, constant ones. So then when we draw our arrow, I can now pass in one of those rotation matrices. So here's rotate, translate, and one thing that you have to keep in mind is that, yeah, we'll talk about that later first. So here's the original, that's what we had originally. Here's the translated, which is translated to -4 and in the y direction and 2 in the x direction. So our translation here is 2 minus 4, and here our arrow was rotated by, what did I say, 140 degrees. Now the nice thing about the common representation as matrices is that we can compound translations and rotations. So if I have a shape and at first I translate it, then I rotate around the origin, then I translate it again, then I rotate it around the origin, then all of that will end up being a 4x4 matrix in 3D or a 3x3 matrix in 2D, right? Now the important thing is that you have to be careful about the order of your operators. So if you have an object and you rotate it first and then translate it, then that's very different from translating it first and then rotating it. So here, if we move to there first and then first, if we rotate it and then translate it, we end up with this yellow shape. If I translate it first and then rotate it, I end up with the cyan shape here. Now, the correct order, because matrix multiplication is not commutative, A multiplied by B for matrices A and B is not always the same as B multiplied by A. Sometimes it is just by luck, but usually it's not. So if we look at our equations here, then we take in the points, we apply our transformation A, and then we get a new set of points. Now, if I want to do this first, this rotation here first, then the translation, then that means the translation must be applied to these points here. So that means we must left multiply our points, our compound transformation matrices. So remember that the transformation matrices must be left multiplied. So far we looked at rotation translation only. I'm going to discuss a couple of other translations, transformations, affine transformations, transformations that keep parallel lines parallel and lines will be lines, remain lines. This particular matrix here with Sx and Sy, then if we apply that, then our coordinates will be Sx multiplied by x plus 0 times y plus 0 times 1, which is Sx multiplied by x, Sy multiplied by y here. So that means that all the coordinates will be multiplied by some constant. If we do that, then that's the effect of this will be either to zoom in or zoom out of the image. We're basically scaling the image, making it smaller or bigger. And then we also have, lastly, the skewing operator. Skewing has ones here, so we get x, y, and 1 here. But then I get x plus kx multiplied by y. Here I get ky multiplied by x plus y. This one is wrong, that should be a 0. That's what the skew matrices look like. Now skewing is sort of when you tilt the image like that. Either this would be skewing along the y-axis or shifting it up and down on one side. That will be shifting it along the x-axis. So here are some examples of scale and skew operations. Here is my original arrow. Here I scaled y by a factor of 2 and x by a factor of 0.5. So now my arrow is shrunk and much longer, but it's still aligned with the coordinate axis, and here the arrow is skewed in the y direction, so x multiplied by ky. So here's our scale, x multiplied by 0.5, y multiplied by 2, our skew, x by 1.5, y multiplied, and no skew in the y direction applied. So now with this you can do some pretty nice results. So here we can draw our arrow, but now I don't just want to draw one arrow, I draw 20 arrows at the position, and my transformation matrix, I keep changing it. So I take the transformation matrix, scale it by 0.8 and 1.1. So the arrow is going to become thinner and a little bit longer. Then I translate it, and then I rotate it by minus 15 degrees. So I rotate it turning to the right, and then I skew it. And this, then I draw the next arrow. So then you can do graphics like that. So here's our arrow and starts off, and we draw a 20 version of this. Now in 3D, it's basically very similar, except we have now 3 coordinates and we need one constant. So we have a 4x4 instead of a 3x3 matrix when we're dealing with homogeneous coordinates. Our translation, scaling, and skewing transformation matrices can take 3 parameters instead of just 2, because we have 3 axes. So I can scale x, scale y, but I can also scale z, or skew x and y and z. And in order to do the rotation, we need to do the simplest way of representing is by rotation around the axis. But there will be 3 different rotation matrices then, one for the x-axis, the y-axis, and the z-axis. And then we can also do some random transformations. And just put them all together. Because basically any matrix that is of that form, 3x3 would be 6 numbers and then 0, 0, 1 at the bottom. That is a affine transformation matrix. It can result as the compound of transformations and rotations and skews and scales. So then I can pick any 6 numbers and I can see what happens to the figure if I draw those. So far we discussed rotation around the origin, but of course we don't always want to rotate around the origin. Sometimes here the orange one is rotation around the origin, right? Sometimes I want to rotate around a different point. So here I rotate around the point 0.5, 4.0, right? And then I get the green arrow. So the question is, how do we do that? It's actually pretty straightforward. First, we take the point and move it to the origin. Then I rotate the point around the origin. I rotate the shape around the origin. Then I move it back to where it started, to the original point. So if I want to rotate around point XR, YR, then I have to take this point and move it to the origin, which means that we have to translate by minus XR minus YR. That will be the first transformation that we need to make. Then we rotate by theta, and then I move the point back to XR, YR, which means we translate XR, YR. So now that the rotation around an arbitrary point can be broken down into a translation by the inverse, the rotation, and then another translation back to where the point should occur. And this is exactly how I implemented that. In this point. Now later on we'll look more into translation of points and origins, but that's it as far as homogeneous coordinates are concerned. One thing that you may have seen is another extension of the formalism. So far we have only shown coordinates, homogeneous coordinates. With the 1 in the last row. If we're dealing with column vectors. Otherwise the 1 would be, for row vectors, the 1 would be in the last column. But mathematicians use a generalized form of homogeneous coordinates where the last number doesn't have to be 1 always. Where here, instead of a 1, we can have an arbitrary factor k that is applied to the components coordinates x, y, and z. So homogeneous coordinates would be kx, ky, kz, and k. And then we can convert that into 3D coordinates by calculating kx divided by k, ky divided by k, kz divided by k. Now, so this gets us from 4 components back to 3 coordinates. So x, y, z, 1 is a special case with k is equal to 1. Right? The advantage of using the more general form kx, ky, kz, k is twofold. One, you can talk about points at infinity if k is equal to 0. Practically, that may be of interest to mathematicians, but in practice that doesn't really have a big impact, isn't very useful. But most importantly, this form can be used in order to model perspective distortion. Now, perspective distortion is something that is not an affine transformation. It's the effect of any camera with a lens that objects that are further away from the camera look smaller. That's the effect of perspective distortion. And that depends on the distance between the object and the camera. That determines then the size. In order to calculate that, you need to do one division, and based on the distance of the object to the camera. And using homogeneous coordinates in the form kx, ky, kz, k allows us to do that very naturally, which means that for any camera system, all the transformations that we're interested in, we can model by a 4x4 matrix using these generalized forms. If you only have 0, 0, 1 at the bottom, then you cannot model the effect of perspective distortion. You can only model translations, rotations, skews, and scales. But with a little bit of overloading of the representation, we can also model perspective distortion. So this will become important in the computer vision course when we talk about camera calibration. If you're also in the computer vision course, then you'll see that again. Okay, good. So that's it for the homogeneous coordinates and affine transformation. So now I want you to play around with that, and what we want to do is later, next class, we're looking at the kinematics of the humanoid robot in 2D. So I want to be able to draw the servo motors and the links. So for the rest of the class, we'll implement a So we want to draw a little servo motor like this, and we want to fill it. Let's take a dark gray and the white servo horn. Range group. Yeah, okay. And then we want to draw bring this to the front. So you want to draw something like this, where we have links connecting different servo motors. Now, the size of the servos that we want to use is 13 millimeters by 29 millimeters. Here's the text. Yes. So the servo size was 13 by 29 millimeters. Length. And the disc, the rotating disc, the servo horn, (20 millimeters). Okay, so now we want to write functions for draw servo, draw link, that allows us to draw a link or a servo at a particular position and particular orientation. So you don't have to solve the forward kinematics yet. We will do this next class. And that will be in 2D. So draw servo 2D at position and angle, and also draw link 2D at position and angle. Now, as I said, later on, when we do this here, represent position and angle, then similarly for the link, if I want to be able to draw any kind of conversion, then really this would be my matrix, right? So really I want to draw based on a transformation matrix. For 2D it will be a 3 by 3 matrix. So that encodes the position and the angle. And it encodes the position and the angle. And that means without doing any changes to the code, I can also scale up the servo, or I can make it smaller or skew it. Which becomes important. Okay, so that's it for the work today. We're gonna keep working on this for another hour, and then that'll be the end of the class. But now let's take a actually I can do this. So here's homework. So let's take a short break of 12 minutes and then I'll be back. I just need to check on something quickly. And then you can start working on drawing your servo motor and the links between them. Actually, not the links between them, you don't need to do it. Just draw a link and draw a servo motor at various positions, different orientations. And those routines we need when we start solving the forward kinematics of our humanoid robot.